It's about one of the weirdest, most, spooky ideas in all of physics. Quantum entanglement, this bizarre thing where two particles, no matter how far apart, seem linked, instantly connected. And you, our listener, sent in this really great question, this intuition. Could there be some kind of hidden subspace, maybe like the one virtual particles use, linking these entangled particles? It's a really deep thought about how things connect.
It really is. And that's exactly what we're going to unpack today. Our goal is to carefully sort through this, figure out what's solid physics, what's on the cutting edge, maybe a bit speculative, and what's more in the realm of, well, sci-fi inspiration. And we're grounding this discussion in a pretty comprehensive theoretical physics report, so we have a solid base to work from.
Right, so this deep dive is all about connectivity, the fabric of reality itself. We'll cut through some dense stuff to get to those aha moments.
Yeah.
Let's jump in. Okay, so before we can really tackle your idea about subspace, we need to get clear on the two main players here. Entanglement itself and these virtual particles. Got to understand them separately first, right?
Absolutely. Let's start with entanglement. It's probably one of the biggest breaks from classical physics. It really messes with our everyday ideas about locality, things only affecting their immediate surroundings, and realism, the idea that things have definite properties even when we're not looking. This weirdness was really brought into sharp focus back in 1935 by Einstein, Podolsky, and Rosen, the EPR paradox.
Ah, yes, EPR. They were too happy about entanglement, were they?
Yep. Not at all. They thought it implied either impossible, instantaneous action, or that quantum theory was, well, incomplete. They set up this thought experiment. Picture two particles linked, flying apart. Measure one, and boom, you instantly know the state of the other miles away. To them, this meant there had to be some hidden information, hidden variables, deciding the outcomes from the start. Otherwise, how could measuring one instantly tell you about the other without breaking the speed of light?
But it didn't stay just a thought experiment. John Bell came along later, in the 60s.
Exactly. John Bell in 1964. He did something brilliant. He figured out a way to actually test this idea of local realism versus quantum mechanics. He showed that if local realism locality plus these hidden variables was true, then experimental results had to obey a certain mathematical rule, a limit. We call it a Bell inequality.
Okay, a testable prediction.
Right. And crucially, quantum mechanics predicted that under the right experimental conditions, you'd actually violate that inequality. You'd break the rule that local realism imposes.
What happened when they did the experiments?
Well, starting with folks like John Clauser and Elena Aspect, and leading up to these amazing loophole-free tests, the ones that won the Nobel Prize in 2022, the results were crystal clear. Nature violates Bell's inequalities. It sides with quantum mechanics, not local realism.
Wow, so local realism is wrong.
It appears so. That means we have to give up either locality, the idea that influences can't travel faster than light, or realism, the idea that properties exist before measurement, or maybe even both. The spooky action is real, in a sense. The question now is, what is this connection?
Okay, so the connection is real, experimentally proven. But it's easy to misunderstand what that means, isn't it? People immediately think faster than light phones or something.
That's the key misconception. It's absolutely vital to understand that entanglement does not allow faster than light communication. There's something called the no communication theorem that guarantees this. When you measure your particle, the outcome you get is random, pure chance. You can't force it to be spin up or spin down to send a Morse code message, for example.
I see. So you can't control your end to send the signal.
Precisely. The weird correlations only show up later. When you and the person with the other particle get together using normal light speed communication, like a phone call or email, and compare your random results, only then do you see the pattern, the perfect correlation.
So it's a correlation across space, but not a controllable influence. Non-local correlation, not non-local causation.
You've got it. That distinction is critical.
Okay, that clarifies entanglement a lot. Now let's switch gears to the second part of your original question. Virtual particles. Another strange quantum concept.
Definitely strange, but in a different way. The basis here is Heisenberg's uncertainty principle, specifically the version relating energy and time. It basically says you can't know both the exact energy of a system and the exact time it has that energy with perfect precision. For very, very short time intervals, there can be a significant uncertainty in energy.
Like borrowing energy, but you have to pay it back quickly.
That's a good analogy, yeah. And this leads us straight into quantum field theory, or QFT, our best framework for particles and forces.
Right, QFT says particles are just excitations like ripples in underlying fields that fill all of space.
Exactly. And the vacuum, what we think of as empty space, isn't empty in QFT. It's just the lowest energy state of all these fields. But because of the uncertainty principle, this lowest energy state is constantly fizzing, fluctuating. These fluctuations manifest as what we call virtual particles. Think of them as particle-antiparticle pairs that briefly borrow energy from the vacuum to pop into existence and then almost instantly annihilate each other, paying the energy back.
So they aren't really particles like electrons or photons that stick around. They're more like transient effects.
That's a better way to think of it. They're more like the constant quantum jitters of the fields. They're not directly observable, stable entities.
But even if they're just fleeting jitters, they're important, right? They're not just mathematical artifacts.
Oh, absolutely essential. Their collective effects are very real and measurable. For one thing, they mediate fundamental forces, like the electromagnetic force between two electrons happens because they exchange virtual photons.
Okay, so they carry forces.
Yep. And they're also crucial tools in calculations. They appear as internal lines in Feynman diagrams, helping physicists calculate interaction probabilities. And we see their effects indirectly. Things like the Casimir effect, where two neutral metal plates placed very close together in a vacuum are actually pushed together slightly.
Why?
Because there are more virtual particles, more vacuum fluctuations outside the plates than between them, creating a net pressure pushing them inwards. We also see their effects in tiny shifts in atomic energy levels, the Lamb shift, and the magnetic properties of electrons. These calculations only work if you include virtual particles.
Okay, so we have entanglement, a persistent non-local correlation between real particles and virtual particles, transient local fluctuations of quantum fields mediating forces. Now back to the original question. Is the connection in entanglement like the way virtual particles pop in and out?
It's a really creative link to make, but fundamentally the analogy doesn't quite work. They're really in different categories of phenomena.
A category error, you called it? How so?
Well, first, think about what they are. Entanglement is about a relationship between two or more real stable particles. Virtual particles are about the temporary behavior of a single field at one location. Then there's the timescale. Entanglement can persist, theoretically forever, as long as the particles don't interact with anything else. Virtual particles are, by definition, extremely short-lived, their existence limited by the uncertainty principle.
And the locality difference you mentioned.
That's the killer distinction, really. Entanglement is the prime example of quantum non-locality. The Bell tests prove it. Virtual particle exchange, on the other hand, is the mechanism for local interactions in QFT. Forces act locally through these exchanges.
So one is non-local correlation, the other is local force mediation.
Exactly. And maybe finally, their reality. Entangled particles are real things you can, in principle, detect. Virtual particles aren't directly detectable. They're more like calculational tools that represent the underlying field dynamics. So trying to equate them is mixing apples and oranges.
Okay, the direct analogy breaks down. But the feeling behind the question, that there must be some kind of deeper connection, some underlying mechanism for entanglement, that still feels incredibly valid, doesn't it? It can't just be spooky magic.
Oh, absolutely. That intuition is spot on, and it's what drives a huge amount of research in fundamental physics. Physicists are searching for that deeper explanation. What is the nature of this connection?
Which brings us back to this idea of subspace. Let's nail down what we mean by that, because it gets used differently.
Right. In formal physics, particularly quantum mechanics, a subspace is just a mathematical concept. It's part of the abstract space called Hilbert space that holds all possible states of a system. It helps organize possibilities, but it's not a physical place.
Got it. Math tool, not a hidden dimension.
But then there's the science fiction idea of subspace. This is probably closer to what you were thinking of. You see it in Star Trek, other places.
Let's drive. Subspace communication.
Exactly. In sci-fi, it's usually portrayed as a physical realm, sort of parallel to our own, maybe with different physical laws, that allows for shortcuts faster than light travel or communication by dipping into this other domain, like a hidden layer of reality.
Okay, so taking that sci-fi concept, a physical shortcut realm, are there any actual scientific ideas, even speculative ones, that echo that? Anything that provides a kind of shortcut?
Yes, there are actually a couple of candidates coming out of theoretical physics that have a similar flavor, though they're far more rigorous and, well, strange than typical sci-fi.
Okay, what are they?
The first candidate is the idea of extra spatial dimensions. This comes mainly from string theory. String theories, to be mathematically consistent, require more dimensions than the 3 spatial ones we experience. Depending on the version, it could be, 10, 11, even 26 dimensions in total.
Where are they then?
The idea is that these extra dimensions are compactified, curled up incredibly tightly, perhaps on the scale of the Planck length, about 10 to the minus 35 meters. So at every point in our space, there's this tiny, hidden, curled up geometry.
So tiny loops or shapes hidden everywhere.
Sort of, yeah. Mathematicians call them Calabi-Yau manifolds, potentially. And within this framework, you get ideas like brain world scenarios.
Brains, like membranes.
Exactly. The idea is maybe our entire 3D universe is just a brain floating in a higher dimensional space, the bulk. Most particles might be stuck on our brain, but gravity, maybe other things, could potentially leak into the bulk.
And the shortcut.
Well, theoretically, if there were another brain nearby, maybe a particle could tunnel off our brain, travel a shorter distance through the bulk, and tunnel back onto our brain somewhere else, a shortcut via the higher dimensions. We look for signs of this at places like the LHC, like energy seemingly disappearing from collisions.
Fascinating. Okay, what's the second candidate?
The second one involves the topology of spacetime itself. Wormholes.
Einstein-Rosen bridges.
That's the formal name, yes. These are theoretical tunnels or shortcuts through our existing spacetime, connecting 2 distant points. Think of folding a sheet of paper so 2 far-apart points touch the wormhole. Is the tunnel connecting them, potentially through a higher dimension, mathematically speaking? They're valid solutions to Einstein's equations.
But the classic problem is you can't actually go through them, right? They collapse or require impossible stuff.
That's been the major hurdle. The simplest wormhole solutions are non-traversable. They pinch off faster than light could cross them. To make one stable and traversable, the theory says you need something called exotic matter stuff, with negative energy density or negative pressure to prop the throat open.
We haven't found any stable exotic matter.
Not in the amounts needed, no. So large traversable wormholes remain hypothetical, though there's some recent work suggesting maybe microscopic ones could be traversable without it, but it's very speculative.
Okay, so extra dimensions and wormholes both offer potential shortcuts. But the wormhole idea feels structurally more aligned with entanglement, doesn't it? Entanglement connects 2 specific particles, and a wormhole connects 2 specific locations.
That's a really key insight. The structure is suggestive. Wormholes link point A to point B, just like entanglement links particle A to particle B. This parallel makes the wormhole a very tempting candidate for a geometric description of the entanglement connection. And this leads us directly to perhaps the most mind-bending proposal in this whole area.
Okay, I'm ready. Lay it on me.
It's called the ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013.
ER-EPR. Let's break that down.
Right. ER stands for Einstein-Rosen bridge, a wormhole. EPR stands for Einstein-Podolsky-Rosen quantum entanglement. The conjecture proposes a fundamental equivalence. Every pair of entangled quantum particles is connected by an Einstein-Rosen bridge, a wormhole.
Wait, seriously, every entangled pair has a tiny wormhole linking them.
That's the proposal. It's suggesting that the abstract informational connection of entanglement actually has a concrete, physical, geometric structure in spacetime.
So the spookiness is geometry.
In this view, yes. The 2 great mysteries, entanglement and wormholes, might be 2 sides of the same coin, 2 different descriptions of the same underlying reality.
Wow. Where did an idea like that even come from? Sounds almost too neat.
It emerged from studies of black holes and something called the holographic principle, specifically the ADA-CFT correspondence.
Holographic principle, like the universe is a hologram.
Kind of. It suggests that physics inside a volume of space, especially one with gravity, can be fully described by a simpler theory living on the boundary of that space, a theory without gravity. ADA-CFT is the best understood example. Now, consider a specific setup in this ADA-CFT framework. A pair of entangled black holes. In the gravity description, the bulk, these black holes are connected by a wormhole. But in the boundary description, the CFT, this system corresponds to 2 separate quantum systems that are maximally entangled with each other.
Okay, so connection in one picture, entanglement in the other.
Exactly. The insight was maybe the geometric connection, the wormhole in the gravity picture, is the physical manifestation of the quantum entanglement in the boundary picture. If you destroy the entanglement, the wormhole pinches off. ER equals EPR.
So if this isn't just about black holes, if it applies to any entangled particles, what does that mean for reality?
The implications are profound. The biggest one is that space-time itself might be emergent from entanglement. Geometry isn't fundamental. It's stitched together by this web of quantum connections. No entanglement, maybe no smooth spacetime.
Spacetime is built from entanglement.
That's the radical idea. But crucially, for consistency, these ER-EPR wormholes connecting everyday particles must be non-traversable.
Okay. So you still can't use them for faster-than-light communication. It preserves causality.
Precisely. The no communication theorem still holds. You can't jump through the wormhole connecting two entangled electrons in a lab. The correlation exists because of the global geometry, but there's no usable pathway.
And these would be tiny wormholes.
Incredibly tiny, Planck scale, highly quantum objects, not the macroscopic tunnels of sci-fi. Describing them properly would require a full theory of quantum gravity.
Okay, let's connect this back explicitly to your initial question about subspace. Does ER-EPR provide that subspace?
It provides an answer, but it changes the question's premise. Yes, entangled particles are connected, but not through some separate external subspace they dip into. Instead, the connection is the geometry. It's a wormhole, a feature of our own spacetime, albeit a topologically non-trivial one. The subspace isn't another dimension in the sci-fi sense. It's the intricate, wormhole-riddled structure of spacetime itself, revealed by entanglement.
So entanglement doesn't happen in spacetime. Spacetime happens because of entanglement. That's the paradigm shift.
That's the core idea behind ER-EPR, yes. The wormhole is the geometric description of that fundamental quantum link.
Mind blown. Okay, is there any link here, even speculatively, back to the virtual particles we talked about earlier?
Yeah.
You said the analogy was flawed, but maybe?
Surprisingly, yes. There's a potential, though highly speculative, connection. Remember how we said the quantum vacuum isn't empty, but fizzing with virtual particles due to the uncertainty principle?
Yeah, the quantum foam idea.
Exactly. Quantum gravity theories often suggest that at the Planck scale, spacetime itself should fluctuate wildly, a quantum foam, where tiny topological structures, like microscopic wormholes, constantly pop in and out of existence. Now, if ER-EPR is true, then entanglement is equivalent to wormholes. So what if the entanglement that inherently exists between the virtual particle-antiparticle pairs constantly forming in the vacuum? What if that entanglement is these microscopic wormholes?
Whoa. So the vacuum fluctuations, the virtual particles, are simultaneously the constant creation and destruction of tiny entangled wormholes.
That's the speculative leap. In this picture, the vacuum isn't just a sea of virtual particles, it's a roiling ocean of microscopic entangled wormholes. The appearance and disappearance of virtual particles is the churning of this space-time foam, geometrically described.
That ties things together in a really wild way. But you keep saying speculative. This ER-EPR idea, it's elegant, but it's not proven in physics yet, right? What are the problems?
Oh, absolutely not proven. It's a conjecture, a powerful guiding principle, but it faces significant challenges. Theoretically, there are tricky issues. For example, quantum mechanics is linear. You can have superpositions. What's the geometric description of a state that's a superposition of entangled, wormhole, and not entangled, no wormhole? General relativity isn't linear like that. It doesn't handle superpositions of geometries easily.
Okay. What else?
How do wormholes, which naturally connect 2 points, describe the entanglement of 3 or more particles, like GHZ states? Maybe you need more complex, purely quantum geometries, not simple ER bridges. There are also consistency questions when you think about particles being created or destroyed.
And experimentally. Can we
Yes.
test this?
That's the really hard part. Quantitatively, if you try to calculate the energy of a wormhole corresponding to, say, 2 entangled electrons, the energy comes out ridiculously, catastrophically higher than the electron's actual energy. Like 30 orders of magnitude wrong. Something's missing or misunderstood there.
So no building electron wormholes in the lab anytime soon.
Definitely not. Direct detection of Planck-scale wormholes is way beyond us. Any indirect effects would be incredibly tiny. And just to be clear about something you might have heard,
The Google experiment.
right, the Google Sycamore wormhole simulation, that was a quantum computation simulating a highly simplified model related to holographic teleportation and ER-EPR ideas. It was not creating an actual physical wormhole in the lab. It was a simulation on a quantum computer. Important distinction.
Okay, good clarification. This all feels so fundamental. It touches on how we even interpret quantum mechanics itself, doesn't it?
It absolutely does. How you view ER-EPR depends a lot on your preferred interpretation. If you lean towards the Copenhagen interpretation, where the wave function is just a tool for calculating probabilities, you'd likely be skeptical about giving these wormholes a concrete physical reality. Non-locality is just a feature of the math.
But other interpretations might embrace it more.
Potentially. If you prefer the many worlds interpretation where the wave function is real and the universe branches, maybe ER-EPR describes the geometric connections between these correlated branches. Or take Bohmian mechanics, which has hidden variables and explicit non-locality via a pilot wave. Perhaps the ER-EPR wormhole is the geometric manifestation of that non-local pilot wave connection. Each viewpoint casts a different light on what connection means.
So wrapping this all up, we started with your intuition about subspace connecting entangled particles via something like virtual particles, and ended up talking about wormholes stitching spacetime together. Quite a journey.
It really was.
Yeah.
And the key takeaway is that initial analogy between virtual particles and the entanglement connection doesn't hold up because they're different types of phenomena, local versus non-local, transient versus persistent. However, that core intuition that there must be something deeper, some physical basis for the entanglement link, that intuition seems profoundly right, and it's driving cutting-edge physics.
And the leading candidate for that, something deeper, scientifically speaking,
Is the ER-EPR conjecture, the idea that entanglement is geometry, specifically a wormhole connecting the entangled systems. It suggests space-time itself emerges from entanglement.
So just to be super clear for everyone listening, we have the established physics entanglement is real, Bell's theorem proves non-locality, QFT describes particles and forces, GR describes gravity, that's solid. Then we have frontier conjecture, ER-EPR, a powerful, influential idea, but still speculative, guiding the search for quantum gravity. And then we have science fiction things like traversable wormholes for FTL travel, still fiction. The ER-EPR wormholes, crucially, are non-traversable, preserving causality.
An excellent summary of the different levels.
So for you, our listener who sparked this whole deep dive, if you're left with even more questions now, that's fantastic. You're thinking like a physicist. This whole quest is really about finding a unified theory of quantum gravity.
And perhaps the most fascinating thought to leave you with is this. What if the universe is far more interconnected than classical physics ever suggested? What if these ghostly links of entanglement are literally weaving the fabric of space-time around us?
Plenty to ponder there. Maybe next time we can delve into the black hole information paradox or more on holography. Thanks for joining us on this deep dive.